DeepVisus, episode, The Brain's Visual Symphony. How does our brain turn fleeting glimpses of motion and depth into a vivid, seamless experience of the world? Welcome to DeepVisus, where vision meets depth, the series that explores the marvels of human brain. Today, we dive into this question through Stephen Grossberg's Conscious Mind, Resonant Brain, focusing on chapters 9, 10, and 11. These chapters reveal the neural ballet behind tracking objects, navigating spaces, and perceiving depth. Imagine weaving through a crowded market or spotting a friend's familiar gait against a glowing sunset. How does your brain make it all feel effortless? Let's step into the visual cortex to find out. Chapter 9 introduces the visually guided steering, tracking, avoidance, and route selection model, or VISTAs, which unifies how we track moving objects and navigate our surroundings. Picture yourself chasing a soccer ball across a field. Your brain's medial temporal and medial superior temporal ventral stream, abbreviated as MTMSDV, uses subtractive processing to isolate the ball's motion from the grassy background, like a spotlight carving out a figure. Meanwhile, as you dodge other players, the medial temporal and medial superior temporal dorsal stream, or MTMSDD, employs additive processing to compute your heading, the direction you're moving. This relies on optic flow, the streaming pattern of the world rushing past, a concept pioneered by psychologist James Gibson in 1950. Movements can distort this flow, twisting a radial pattern into a spiral. Here, an efference copy, a signal from the brain's motor commands, corrects these distortions by subtracting the eye's motion, restoring a clear path. A log polar map in the primary visual cortex, known as V1, further simplifies this by transforming complex flows into parallel signals, helping your brain pinpoint your direction. Chapter 10 explores decision-making, where these motion signals guide choices. Kick the ball or pass it. The saccadic and smooth pursuit eye movement model, or SAC-SPEM, coordinates two types of eye movements. Smooth pursuit eye movements, called SPEMs, keep your gaze locked on the ball, while saccadic eye movements, or SACs, rapidly shift your focus across the field. This coordination, rooted in the superior temporal sulcus, ensures you stay on target. Grossberg's models, tested on stimuli from lab-generated random dots to real-world videos of Boston traffic, show how these circuits handle complex, dynamic scenes with predictive precision. Now, let's venture into three-dimensional vision in Chapter 11, where the 3D layered architecture for matching, attention, and recognition of textures model, or 3D laminart, illuminates depth perception. Imagine staring at a Necker cube, a 2D drawing that flips between two 3D shapes in your mind. Your brain builds these percepts using angle cells, disparity gradient cells, and bipole cells, which group edges and slants to create depth. But what happens when each eye sees conflicting images? This triggers binocular rivalry, where, for example, vertical and horizontal gratings compete for dominance, oscillating in your awareness. The 3D laminar model highlights three key mechanisms: bipole grouping for depth, orientational competition to resolve conflicts, and habituative transmitters that reset perceptions. These same processes ensure stable vision, letting you see a unified world most of the time. Simulations from lab gratings to natural scenes like those from the University of Tsukuba's multi-view database achieve an impressive 96.2% accuracy in reconstructing depth, rivaling advanced machine vision systems. So, how does the brain weave these elements into a coherent visual experience? Chapters 9, 10, and 11 paint a unified picture. The brain is a master orchestrator, using shared neural circuits to process motion, guide navigation, make decisions, and perceive depth. The log polar map in V1 simplifies motion patterns, efference copies correct for eye movements, and bipole grouping constructs 3D scenes. Whether you're tracking a ball, weaving through a market, or puzzling over a Necker cube, your brain transforms raw sensory input into a vivid, conscious world with remarkable precision, all grounded in biologically inspired mechanisms. Yet, the story doesn't end here. How do these circuits adapt to futuristic environments like virtual reality? Can attention reshape our perception of motion or depth in unexpected ways? Join us in upcoming episodes of DeepVisus as we probe deeper into the brain's visual mysteries, uncovering how they shape our reality and inspire tomorrow's innovations. Tune in, let your curiosity lead the way, and let's explore where vision meets depth.